iC-Haus Integrated Circuits.
Hi, this is Silvan, Sales Application Engineer at iC-Haus. Today warmly welcoming you from my desk here in Bodenheim, and this time I'm reaching out to the application programmers and embedded software engineers out there. Are you about to solve a coding task with one of our configurable ICs on your desired microcontroller? Then this episode is for you. I am excited to announce that we are assisting with your embedded software application by providing new tools for our ICs. These new tools are called MCU Drivers. In this video, I'm happy to introduce the concept and content of the MCU Drivers to you before implementing an example application on a real microcontroller. So please find further information on how to get these new tools in the video description below. And before we are getting into embedded C, let's take a short look at the concept. So in this illustration, I have divided a basic embedded software application into abstraction layers. First layer on top is the application layer. Some might call it the code or the program. To be able to implement such sequence of tasks on your desired microcontroller, you will likely make use of a hardware abstraction layer, which we will use the abbreviation HAL for from now on. The HAL basically provides well-readable, powerful functions to interact with a microcontroller on a somewhat higher level. So initializing an interface, controlling GPIOs, transmitting or receiving data, everything is done via one or just a few function calls, making programming so much easier for all of us. And this is basically the concept that we've been following with the MCU drivers. So sitting just between the application layer and the HAL, an additional IC driver layer is established that provides the basic infrastructure to communicate and configure our IC from your desired microcontroller. And to be able to use this software module on your desired architecture, we are following a black box approach here to encapsulate all the MCU-related dependencies. So all you need to do as a user is define the wrapper functions with the hardware characteristics of your microcontroller, and then you're ready to go. Might sound a bit complicated, but it's not. I promise I'll show that in a minute. So without further notice, I do suggest that we go right into the example application and start coding right away. So here's our blank example project ready to get filled with some code. Basic description of what we will be doing. We will configure and read the position of an absolute encoder. More specific for the hardware, we are using an optical reflective encoder IC, the iC-PZ2656, which is mounted on bottom of the PCBA here. This is the eval board PZ1M. We are sampling a 26mm disc with 256 CPR. From the PZ1M, we are going via this blue ribbon cable to its motherboard, the PZ2D. From the motherboard via those brown wires, we are going to an Arduino Uno in revision 3. And from the Arduino via the USB port, we are going right into a computer running Windows 10 operating system. So this is specific for the iC-PZ series. We have to configure the output ports so that the SPI is on port A. Therefore, there are some jumpers on top of the eval board PZ1M, and I've configured those jumpers to low, 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 which means that the SPI is on port A. Then we are connecting port A of the iC-PZ via those brown wires to the SPI master, which is the Arduino Uno. The iC-PZ is supplied through the 5 volts output of the Arduino. So going to the clamp here, and I am connecting both supply voltages of the iC-PZ through jumpers 1 and 2. So basically all the components are supplied through 5 volts USB. As software, we are using the Arduino IDE that you are seeing here. It's version 1.8.16. Arduino tools are open source and a great start into the world of embedded software applications. And this video is about the 1SF drivers, and we are using the PZ1SF driver version 1.1.0. So before we could use the driver, we need to do some preparation. And step one would be, of course, to put our source code files of the driver into our existing project folder. I've opened both already. So on the left side, you can see the content of the 1SF driver, so the package that you are receiving from us. We do have an HTML style documentation that you can access on your desired browser via manual.html. Then we do have the end user license agreement as for all our software. And most important for us, of course, are the source code files, which you can find in the SRC folder. And all I'm doing is grabbing both files, pressing Ctrl+C and pasting them into my existing project folder on the right side. So that's it for the first step. Then we need to manage our includes. I've included the stdint simply because I'm very used to using stdint. Then we need to include the SPI library of the Arduino, and as a last include, we of course need to include the header file of our PZ1SF driver. That's it for our includes. As a third step, we have to set up our Arduino interfaces. In particular, I'm using the SPI interface, of course, and also the USB interface to later on display the data that I'm receiving via SPI. So what I've done is defining the chip select pin, which is pin number 10. So this is simply a GPIO. And then there is the setup function, which is kind of an initialize function for the Arduino. And we are just configuring the chip select pin as output. And then we are initializing our SPI module via spi.begin and also our USB module via serial.begin. So that's it for initializing the interfaces. As a last and very important step for the preparation, we need to define the wrapper functions of the 1SF driver I have mentioned earlier. So before doing so, let's have a quite short look into the header file of the PZ1SF driver together. When scrolling down a little, quite on top of that file, there is the group of wrapper functions, which you can identify by the keyword extern, by the way. Let me explain this a little. So there is a function declaration available, but the definition is not. And this is what we have to do as a user according to the individual hardware that we are using. So I am grabbing this function prototype, pressing Ctrl+C and pasting it into my existing project. So now I'm opening the brackets so that I am ready for a function definition. So for the definition of our SPI transfer function, we of course need to select our SPI slave at the very first. So and this is done via digital write, and then as you remember, we do have a define for our chip select pin, and then we just pull this low. So the SPI slave is selected for communication now. And as the Arduino is an 8-bit architecture, we are going byte by byte SPI data transfers. And therefore we are using a for loop. So we say for uint8t, and then we define a counter initialized with 0. Then we go counter smaller data size, and then we just increment it. And what we will be doing in each of those iterations is to receive 1 byte of the RX buffer and to transfer 1 byte of the TX buffer. So quickly checking if I have done a mistake here. Reads well, so let's go ahead. Last and final line that we have to include is of course to pull the chip select high again. And this is done by the equivalent of pulling it low. So we just copy paste it and replace the low with high. So that's it for our SPI transfer wrapper function. And with this definition, we are ready to use the driver. So now we are ready to program our task with the IZPZ2656. And what I'd like to do for demonstration purposes is to manipulate and set the position data format, and then read and display the absolute position. And to set the position data format, I have implemented some defines here according to the table in the datasheet that you can see on the right side. So we are not using SPI extended, so this is set to 0. Then we are defining the multi-turn data length to 0 bits, so no multi-turn is used for this example. We are configuring the single-turn data to 16-bit, and then we have 8-bit in total for the error bit, warning bit, and the 6-bit CRC. So that makes 3 bytes for our position buff size. To write our position data format configuration to the on-chip RAM now, I'm making use of functions provided by the 1SF driver. So I've implemented this already. Let's scroll down a little. Here in the loop function, which is kind of equivalent to int main, I am using the pzWrite parameter function to write a value to a specific parameter. Let's quickly find this function in the header file. So those functions are provided by the 1SF driver. The functions basic are kind of equivalent to the opcodes given in the IZPZ series datasheet, and there are also advanced functions like reading or writing parameters. And this is what I'm using here. I'm simply passing the parameter, which is given by the 1SF driver as well, and then I'm setting it to the value that we have defined above. And then good practice would be to just read back what you have written and check if it is the value that you are expecting. And if not, then do some error handling. And I've done this for all the 3 parameters that we want to write. So here is the multi-turn data length, here is the single-turn data length, and then we are ready to read out the position that we have just configured here. Now with the position data format configured, we are ready to read the position and finally display it in the Arduino IDE. So I have implemented this already in our loop below. So we are entering a while loop that we're never going to leave because we want to read the position as fast as possible for this demonstration. First thing we need to do here is to declare a position data buffer of the size that we have just defined above. As you can remember, we do have 3 bytes in total for our position data. Then we are calling the pzReadPosition function that is provided by the 1SF driver. We're just passing the buffer the position data should be written to, and then we're passing as a second argument the size of the buffer. So when now the position is received and written to the buffer, I am extracting the relevant part for us, which is the single-turn position in this case. And as you can remember, we do have 16 bits data length for the single-turn position. So I'm using a uint16 and grab my MSB in the array at 0 and shift it 8 bits to the left. Do not forget to cast it to a uint16, otherwise the shifting will fail. And then I OR it with the LSB that is stored in index 1. And then I'm having my complete single-turn position data word. And last thing I'm doing then is printing it in the Arduino IDE via the very handy serial module. So this is just one line, serial.println. Then I'm throwing in my data that I want to print, and I'm giving it a format. We want to print it in decimal. So let's compile it and see what we are getting when starting our drive. So our sketch has just been compiled without any errors. I have already uploaded it to the Arduino, and we are now ready to display the singleton position in the Arduino IDE. Therefore, I'm going to Tools on top, open the serial plotter, and there you can see quite a flat line. And when I'm switching on the drive now, you will see the singleton position information that you are used to when working with encoders. Okay, here we are. Here are our position ramps, and that should conclude our application example with the 1SF driver. If you do have any further questions, feel free to reach out to me via contact details in the video description below. I say thank you for watching and feel free to tune in next time.
iC-Haus. Integrated circuits.